So, welcome again to the new lecture of the course Fundamentals and Applications of Dielectric Ceramics. Let's just briefly recap the previous lecture. So, in the previous lecture we finished our discussion on phase transitions in ferroelectric materials. So, basically the take home message for that is that in the second order phase transition, the polarization drops gradually near Tc until Tc, and the susceptibility shows a 1 over chi shows a decreasing behavior as it approaches from paraelectric to ferroelectric region. So, this region is ferroelectric and this region is paraelectric, right, and this is basically you can say the boundary between the two, and this is for second order, right, and this is because, and this is also manifested in the free energy, second derivative of free energy showing a discontinuity, whereas first derivative is continuous. So, as a result there is no latent yield involved in this transition. If you look at the first order shows a different behavior. In the first order, when you plot P versus T, the polarization suddenly drops to 0 at Tc. Okay. So, this is abrupt change in polarization, and the susceptibility change is manifested in this fashion. So, this is a change in susceptibility with susceptibility of high temperature region extrapolating back to a temperature T0, and between T0 and Tc we have one more subsidiary minima in free energy landscape between these two temperatures, and in this again this is ferroelectric region and this is paraelectric region, and this is manifested in the first derivative of free energy being discontinuous or entropy being discontinuous. Okay. Now, let us and we also started our discussion little bit on switching in ferroelectrics, where we looked at the ferroelectric hysteresis loop, which shows a behavior like this. So, and now we are going to talk about the microscopic mechanisms of why do we get such a behavior in ferroelectric switching. So, we saw for such a switching behavior because in the beginning you change your ferroelectric hysteresis like this, and then once it achieves a saturation, when you bring it back to lower fields, then the polarization does not come back to initial state, rather it goes to a state PR state. So, question is, what is the reason? The reason for these, as we said, lies in domains. So, we will start our discussion on domains, or rather ferroelectric domains. So, as we said, ferroelectric domain is basically, if you take a crystal, small crystal, and if all the polarization vectors are aligned in one direction, then this will be called as monodomain state. Okay. So, all the polarization vectors. So, basically a domain is a region in which the polarization of all the polarization vectors or all the dipoles are aligned in one direction. So, that is called as a domain, and domain is not a grain boundary, is not to be confused with the grain boundary. Grain boundary is about crystal orientation, the differences in crystal orientations of neighboring grains, where domains is about the polarization orientation with respect to applied field and polarization orientation within a particular region. So, it is possible that within a grain you can have multiple domains. It is also possible that when you apply large electric field, despite having several grains, the whole material becomes in monodomain state. So, it is not to be confused with the grain boundaries. So, domain is basically a region of single orientation of polarization, right. Now, so when you start from, let us say, cubic system, let us say you have cubic material, and if you cool it below Tc, so this is paraelectric state, right, paraelectric state, when you cool it below Tc, the system transforms, let us say it becomes tetragonal, right. So, your C parameter becomes little larger than the A parameter, as a result you have some distortion. Now, what may happen in this system is that, since if you have a monodomain, let us say you convert in this fashion and you think that all the dipoles are now aligned in this direction, because the polar axis in such a material, let us say if it is a case of barium titanate, then the polar axis in such a material will be along the C axis, which is 001 axis. So, polar axis is in ferroelectric state is C axis. So, you would say that you would assume that all the polarization vectors will be aligned in one direction. Now, if all these polarization vectors are aligned in one direction, you will have massive surface charge density. So, you will have all the negative charges aligned here and all the positive charges aligned here. So, you will have massive surface charge density on the surfaces of crystal. Suppose this crystal is of the order of 1 centimeter by 1 centimeter by 1 centimeter. In terms of dimensions, this means massive charge density, right. This massive charge density leads to creation of what we call as a depolarization field. So, depolarization field is something which would like to minimize the surface charge density. So, this single orientation of polarization sets up what we call as depolarizing field, and this depolarizing field will oppose the polarization. So, while all the dipoles would like to align in one direction, there will be massive surface charge density. As a result, electrostatic energy will increase, and this will lead to depolarization of charges. So, these two act in competition with each other. Eventually, what will happen, because of competition of polarization energy and depolarization energy, the system will transform into a situation something like this. Let us say, if I now create a situation in which I have two regions within the same crystal, one with orientation P like this, another with orientation P like this, then this will have surface charge density in this fashion. So, now the net surface charge density has gone down, but while the net surface charge density has gone down, we have created an interface between the two. So, this is a surface, extra surfaces always cost energy. So, it is a competition between also the depolarizing. So, depolarizing energy has to, reduction in the electrostatic energy due to depolarizing field has to compete with the surface energy, right. So, on one hand we are going to reduce electrostatic energy by having depolarizing field, which will prevent charges build up. On the other hand, we will increase surface energy, which is in the form of domain wall. So, which is in the form of domain wall, which is basically the interface between the two. Just like a grain boundary, you will have a domain wall energy. So, these domains are created. Now, the type of domains which are created will depend upon the type of material. So, for example, if you have a tetragonal crystal, you will create 180-degree domain walls and you will create 90-degree domain walls. But if you have, for example, rhombohedral crystal such as lead zirconate titanate, this is rhombohedral, this will give rise to 180-degree domains, also 71-degree domains and 109-degree domains. So, depending upon the type of crystal system that we have, you will have different types of domains in the system. Okay. So, as I said, it is a competition between the depolarization energy. So, competition between depolarization energy, which minimizes the electrostatic energy, and the domain wall energy or the domain energy, will, so one is negative, another is positive, will lead to a stable domain size, which means we need to deal with the energetics of the process, right. So, for a ferroelectric crystal we express the energy as, so the free energy change, that is we can write the free energy change upon formation of domains as, so if you write delta G, which is G minus G naught, which will be, it's composed of few energies. One is, let us say, UC, another is UP, another is UX, another is UW, another is UD. So, let us say UC is the energy which is effect of applied field, okay. On domain energy. UW is basically UP, and UP is basically bulk, let us say, electrical energy, and this is bulk elastic energy, right. So, these are basically material dependent parameters. For a given material you will have certain electrical energy and elastic energy. Then UW is what we call as domain wall energy, or right now we will write as a domain energy, and UD is nothing but depolarizing energy related to depolarization, okay. So, you can say it is depolarization related energy, okay. To get a stable domain structure, this delta G versus, let us say, D of delta G versus, if the domain size is delta, this has to be equal to 0, which means delta G is minimum for a stable delta, that is the stable domain size, where delta is the domain size, okay. So, basically these materials UX, UP, they are material parameters, they are same in each domain, and UC is effect of applied field. These energies can be treated as constant. So, these energies do not vary much depending upon the domain size. So, these we can treat as constant, okay. So, we can write this delta G as a constant, let us say A, okay, or just say U naught, which is a constant, plus UW plus UD. UW, the expression is gamma, which is the surface energy, domain wall energy, multiplied by the volume, divided by the delta, which is the domain wall, domain thickness, domain width. So, this is you can say surface domain wall energy. So, this is wall energy, interfacial energy basically, this is volume, crystal volume, and this is domain width, okay. So, this is the expression for we can say that UW. UD on the other hand is given as epsilon star into delta into V into P naught square, that is the polarization at the center of the domain, and then divided by thickness, which is the crystal thickness of crystal. This is polarization in the middle of the crystal, in the middle of the domain. This is dielectric constant, and so this is dielectric constant. V is the volume, delta is the domain width. Now, what we are going to do is that we are going to take a derivative of this delta G with respect to, so we take d of delta G with respect to d of delta, and this must be equal to 0. So, when we do that, what we get is we get epsilon star into V into P naught square divided by T minus of gamma into V into delta square, this is equal to 0, right. So, from this we determine delta as gamma T divided by epsilon naught P naught to the power 1 by T. This is the stable domain wall width that you get in ferroelectric material. So, you can see here this delta is proportional to gamma. So, which means higher the interfacial energy is, smaller will be bigger will be the domain size. That makes sense. Higher the interfacial energy is, so this is like grain boundaries. Higher the grain boundary energy is, larger the grain size is, because you would like to minimize the surface energy. So, any increase in gamma will prefer bigger domains. Similarly, if you make the crystal thicker, which means the net, so this is like charge density, the charge density per unit volume of the crystal also goes down, which means you can manage with bigger domains. The electric constant, if you increase the electric constant of the material, so this is the epsilon star, if you increase the electric constant of the material, which means you will polarize the material more, which means you will have more depolarizing energy, which means you would have smaller domains. Higher the polarization, again this is P naught square, sorry, just one second, and higher the polarization, again you will have more separation of the charges. As a result, you will have more charge density, which will create more depolarizing energy, and as a result, so basically these two factors lead to larger delta and these two factors lead to smaller delta, and this is the surface energy term, and this is the term which is related to polarization or depolarization energy of the material. So, this is the stable domain size that you get in the material essentially. Now, different type of crystals will give you, how does it look macroscopically? Microscopically. So, suppose you have a crystal like this, okay, in which you have these multiple regions, okay. So, crystal at the center, the central atom, in this case all of them have this orientation, right. It is moved up from the central position. So, this is all pointing up. Okay. Creation of a domain wall, let us say at this point. So, if you create domain wall here, then this leads to formation of a slightly different So, what will happen is that in these two regions the atom will remain shifted up, in these regions we will have atom shifted down because the polarization is now shifted. So, these regions will have up, in these regions it will be down, and somewhere in these two, in the regions in the middle, there will be a change in the domain wall. So, these regions will have some variation. So, you might have little bit of sort of intermediate positions somewhere here. So, this region will be the domain wall, the region of disturbance along which the orientation changes, because you have this change in orientation from here to here. These changes will not be abrupt, they will be little random. So, as a result, each domain wall will also have domain wall width, which is sort of the order of a unit cell or so. They are much more sharper than magnetic domain walls, but there will be a region in which they will have to go transition from up to down. So, there could be about a unit cell across which the transition occurs. Okay. So, this is basically a domain wall. As I said, domain walls are of multiple types. So, you can have, in this case I have shown you 180 degree domain walls, but there is a possibility that you might create something like this. You might have a crystal in which let us say something like this. So I just wanted to show okay, so I just wanted to show 90-degree domain walls. So let's say the orientation in this case is like this, and this is a domain wall that you create in between. So in this case this atom may be sitting right at the center, whereas in these regions the domain the polarization may be in this direction. So here the P is like this, in this case the P could be like this. So this is P down in all the way. So there will be a gradual transition within this region. So this will be domain wall with gradual change, right. So as I said, there are multiple domain walls in tetragonal crystals. Generally we observe 90-degree domain walls like this. So this is a 90-degree domain wall because polarization changes from this to this. So this is P, this is P, and 180-degree domain walls in which, so this is like this. In this case it would be like this, but depending upon the crystal orientation you may have multiple orientations, and there are some nice papers available on which you can see that different crystals will show different orientations. So, so domain wall type, domain wall angle would be determined by crystal system, okay. But generally when we talk of tetragonal crystals we talk of 90-degree and 180-degree domains. So now let us see, once we know how the domains form, basically what happens in case of free energy, in case of switching is essentially when you start switching, okay. So you start at this point PE, in this material at this point A, although material has domains, but it is in the polycrystalline state. So you might have a material, these are the grains, okay. Now these grains will have domains, let us say domain distribution is something like this, assuming that domain size is, so red ones are domain boundaries. Now it might happen that the polarization vectors are rotated randomly. So we have random domain orientation. As a result, sigma mu is equal to 0. So you have 0 polarization. So in this state you can say that number of this and this are equal, okay. So P up is equal to P down, okay, 0 polarization. As you start switching it in the linear region, you just create polarization because of electric field associated polarization. So this is the linear region. When you increase the electric field, what you do is that in these crystals, let us say we apply the electric field in this direction, we start nucleating new domains of the which are oriented along the direction of electric field. So what will happen is that, let us say these are the few domains, we will start nucleating new domains in this direction which are oriented in this direction, and they are generally created at the interfaces. So at this point we will have nucleation of new favorably oriented domains, okay. And up to this point, up to which all of them are oriented, they will keep increasing in size at the expense of old domains. So these domains will keep growing as you increase the strength of electric field in this direction, irrespective of the orientation of previous domain. Previous domain could have been like this, but the new domains are all oriented along the electric field. So basically this region is the region in which growth of new domains which will consume the old domains, something like Ostwald ripening. Once all the domains are oriented, again you will have a change in linear region. So, this is where we will have a state in which whole material will be in this state, monodomain state. Okay. So, what might happen is that initially you might form a domain which is slightly tilted to E, which starts nucleating. Finally, the domain will also orient towards the electric field. So, once you reach a monodomain state, when you switch off the electric field at 0, the domains do not get back. So, only some of the domains get back to previous different orientations, but not all domains come back. So, what might happen at this point is you will have a crystal in which have, so I am not going to draw the grains, I am just going, sorry, I am just going to draw the domains, I am not going to draw the grain boundaries, okay, just the domains. So, what might happen now is that let us say our electric field is now 0, but most of the domains remain oriented in this direction, very few domains come back in this direction. So, as a result your net mu is not equal to 0 and you have basically more polarization in this direction than in this direction. So, basically sigma p is not equal to 0. So, that is where you cause remanent polarization. Now, to bring all the domains back to 0, back to this orientation, you need to apply a field which is called as coercive field. At this point then number of, if you now look at the bigger picture, number of domains which are oriented in this direction and number of domains which are oriented in this direction, this is the sort of state you want to achieve when sigma mu is equal to 0. So, oppositely oriented domains are equal in fraction, and then again the same process repeats as you go in the negative cycle. So, this is how the switching occurs in ferroelectrics, by formation of new favorably oriented domains to the direction of applied electric field and their growth, and then saturation. When all the domains get aligned, there is nothing more to be aligned, you basically saturate the polarization, but when you come back to 0 electric field, the domains do not revert back to original position. Okay. You can say it is because of friction in the lattice or whatever, but they do not get back to their original position, and to bring them back to original configuration of equal domain proportion of opposite types, you will have to apply an extra electric field which is called as coercive field. That is why it is coercive. English word coercive means coercion. You are forcing the material back to 0 polarization by applying an extra electric field. And these states are, by the way, equal and opposite. So, plus EC and minus EC are equal in magnitude. Similarly, plus PR minus PR are equal, plus PS and minus PS are equal and opposite, because material for a given material for a limited volume. So, in this lecture what we have done is we have looked at the domains in ferroelectric materials, their origin and how they play an important role in switching, and that is why they give rise to a hysteresis that we observe. So, we will stop here, and in the next lecture we will finish our discussion on ferroelectrics, and we will of piezoelectric, pyroelectric and ferroelectric materials. Okay. Thank you very much.